To train multilingual AI models, companies spend millions on pure compute. Managing the sheer scale of these neural networks has become a massive budgeting problem. Optimizing large pre-trained models for specialized tasks currently demands enormous GPU clusters running relentlessly for weeks at a time. But there is a mechanical shortcut. It is a surgical operation called trimming, and it specifically targets a model's embedding layers to cut out unused linguistic data. Trimming completely ignores the core reasoning backbone of the transformer. Instead, it exclusively modifies the final output layer and the model's vocabulary mapping. A standard open-source model comes preloaded with tens of thousands of tokens. Tokens for Arabic, tokens for Korean, or tokens for Dutch. If an engineering team is building an English-only application, they are carrying millions of parameters for text their system will never process. Excising those unused tokens creates a hyper-efficient alternative to traditional distillation. The entire process executes in minutes on a standard consumer CPU, while preserving the model's high-end benchmark scores. To see exactly how much dead weight can be removed, we can map the architecture of a baseline model like GPT-2 Small. This diagram highlights the 12 transformer blocks, which remain locked and untouched. The target is the embedding matrix, labeled WTE weight. In GPT-2, this matrix has a dimension of 50,257 tokens by 768 dimensions. That vocabulary size of 50,257 is inefficient for modern hardware. GPUs execute matrix multiplication significantly faster when the matrix dimensions are multiples of 64 or 8. By reducing the original vocabulary down to exactly 32,768 tokens, we slice off over 13 million parameters. The model's total size immediately drops by nearly 11%. This surgical cut aligns the vocabulary to hardware-native multiples, optimizing memory allocation and tensor core utilization, and it achieves this without altering a single mathematical weight in the model's core layers. This technique is highly effective, but it is bound by a strict architectural constraint. We can see this limitation when analyzing models like Google's Gemma. This schematic shows a network stack where the embedding layer is positioned at the bottom, but two heavy, dense layers are stacked directly on top of it. Because the embedding layer is buried beneath these classification blocks, trimming the vocabulary severs the mathematical pathways required by the top layers. This is the re-ranker rule. If a model uses a classification head over the embeddings, trimming will cause a massive performance collapse. The engineering checklist is binary. You can only trim a model if the embedding layer operates as the absolute final output of the network. When the architecture does allow for it, trimming competes directly with complex distillation methods. We can test this by pitting DistillBERT against a surgically trimmed version of MMBERT Small. This chart displays parameter counts for both models. DistillBERT requires 67 million. The trimmed MMBERT Small needs only 54.8 million. Adding performance scores, the trimmed model outperforms the distilled version on the GLU benchmark, scoring 81.5 against DistillBERT's 79.5. The trimmed model also processes a significantly larger context window, handling 8,192 tokens compared to DistillBERT's 512. Creating DistillBERT required roughly 90 hours of continuous GPU training. Extracting the trimmed MMBERT Small required exactly 9 minutes of token mining on a standard CPU. To maximize these gains, engineers execute a trim then fine-tune protocol. Shrinking the model first ensures the subsequent fine-tuning pass runs much faster, allowing the model to process more data on the exact same compute budget. For tasks requiring a single language, trimming yields a superior, more capable model in a fraction of the time needed for traditional distillation. Executing this process requires answering the retainment question. Exactly how many tokens must be kept in the new vocabulary to prevent the model from losing comprehension? This graph plots tokens retained against dataset coverage for English. The curve plateaus at 32,768 tokens, capturing 99% of the data. Overlaying the Korean curve changes the math. It hits 99% early, but capturing the final 1% requires an additional 140,000 tokens. To map these curves accurately, engineers parse text through the model using datasets like FineWeb 2, measuring which tokens appear most frequently. The size of the trimmed vocabulary must be calibrated to the orthographic complexity of the target language. Cutting too deeply into the long tail of a complex alphabet destroys linguistic nuance. This structural resilience extends beyond text generation. Trimming is highly effective on visual embedding architectures like CLIP, particularly in zero-shot image classification. To prove this, researchers ran a classification experiment using this aerial view of Paris, testing if a model stripped down to a Spanish-only vocabulary could still accurately recognize concepts in other languages. This data visualization tracks the total memory size of MetaClip 2. The original 32-bit model requires nearly 1,500 megabytes. By stacking trimming with 16-bit quantization, the total footprint shrinks to just 94 megabytes. Despite this 93% reduction in mass, the trimmed Spanish model identified the image with classification scores identical to the original, down to 15 decimal places. Trimming does not replace quantization. It is a structural multiplier that makes standard quantization methods exponentially more effective. This three-tier hierarchy chart defines the optimal engineering pipeline. At the top is the gold standard, a monolingual model trained entirely from scratch. In the middle is the silver tier, a large multilingual model that has been trimmed and quantized. Traditional distillation sits at the bottom. Training a model from scratch takes months of testing and iteration. Trimming serves as an immediate, mathematically sound stopgap for specialized languages while those bespoke models are still compiling. By executing a 9-minute CPU pass on a pre-trained embedding matrix, developers completely bypass weeks of complex GPU optimization. Audit your embedding layers. Align your vocabulary dimensions to hardware-native multiples. An untrimmed model is carrying dead weight, and in machine learning, dead weight costs compute.